the day before Thanksgiving. Sure. Today's the last sorting lecture, and so I promised you 8 sorting algorithms this class, and we've got 2 to go. First, we're going to start today with counting sort, which is very similar to bucket sort. You use it in a slightly different situation. Bucket sort is particularly good for linked lists. Counting sort does essentially the same thing bucket sort does, but it's better when you have arrays that you sort. So we'll look at 2 versions of counting sort. Let's start out with the simple version where all you want to sort is a bunch of naked keys, and there are no records associated with the keys that you want to sort. Gives us a really easy sorting algorithm. You just count how many occurrences there are of each key. So unlike bucket sort, we don't need any queues. We just count the number of copies of each key. And then we translate that count into a sorted output array. So here's how we do it. Suppose that the array looks like this. We want to sort 6703150337. What I'm going to do is I'm going to have an array of counters, one for each possible key. And of course, just like bucket sort, for this to work, there can't be very many possible keys. So I'm going to start with all of the counts set to 0 and then just walk through my input array and count keys. So I've got a 6. That's 1 in the 6 box. I've got a 7. I've got a 3. I've got a 0. I've got another 3. So the 3 box now goes up to 2. I've got a 1. And a 5. Another 0. Another 3. And 7. And so now this is what my counts array looks like when I'm done. And to do the output, I just walk through the counts array from start to finish and output that many of each key. So it says that I have 2 0 keys, so I output 2 zeros. I have 1 1 key, I have no 2 keys, I have 3 3 keys, so let's write 3 3s. No 4s, 1 5 key, 1 6, 2 7 keys. And that's that. Any questions? Yeah?
So the range of keys has to be finite.
Yeah, so this is just like bucket sort. The range of keys has to be finite, and to make it fast enough to even be worth considering, the range of keys has to be really small, like on the order of n or smaller. Yeah, other questions? And we will, by the end of this lecture, fix that problem. But before we do, this is kind of limited, what I've shown you so far, because it only works if you have keys that have no associated information that you have to sort as well. Now, what if you're sorting database records and you're sorting them on, a list of people who are your employees based on their salary or something like that? Then this by itself isn't going to work. And if you look at it, at first it doesn't seem like there's a way to get it to work. But there is. It's tricky, but we'll see how to do it. Now I'm going to do counting sort with complete items, where a complete item consists of both a key and some sort of associated values, which might be a whole database record. this, we definitely need a more elaborate version of counting sort. So let's start off with, let X be an input array. And now it's not just an array of numbers, it's an array of objects that happen to have keys among other things stored in them. So there's your database records. And your array X maybe looks something like this. Same numbers as before. But now, each of these is actually an object that can have all sorts of other information in it as well. Now, we're going to start the same way we did in our original counting sort. We're going to count all the keys. And I'm going to give you a complete implementation of this advanced counting sort. So let's look at the first few lines of code. Okay, so it's a very simple idea, but when you write it out in code, you'll notice that we have an array indirection inside another array reference. So that's kind of interesting, especially since by the time we finish this algorithm, we'll have a triple indirection in one loop. So now we have the counts array again. And initially, the counts array is going to come out the same as before. So we do our counts and we get 2, 1, 0, 3, 0, 1, 1, 2, just like before. The next thing we're going to do is something called a scan of this array. And what a scan does is it walks through the array and it adds up the numbers. And the purpose of doing this is to make sure that when we're done, this array element here is going to contain the place in the output array where I should put the first database record whose key is 2. This one is going to tell me where in the output array I should put the first database record whose key is 5, and so on. And the way you do that is you add up all the numbers to the right of your current position. So after the scan is done, counts I contains not the number of keys that are equal to I, but it contains the number of keys that are less than I. So what does that mean? Well, I want this box, the 7 box, to have a count of how many keys are less than 7. So that means I add up all of these boxes. That's 3, 6, 7, 8, and I write an 8 into that box. And this one, everything to the right adds up to 7. This one's going to be 6, this one's going to be 6, this one's going to be 3, this one's 3, this one's 2, and the first box is always 0 because there are no keys less than 0. Now, I just did that scan from right to left because for a human it's easier to see what's going on when you do it that way, but that would take quadratic time. The computer actually does it from left to right, and that takes linear time. And it's a very simple loop. It looks like this. We're going to keep a running total as we go from left to right. And we're just going to loop through the counts array once. And as we go, we're going to save whatever is stored in the current array element. We're going to replace it with the total, which is the sum of all of the counts to the left. And then we're going to add the new value to the total, so that it's ready to go for the next iteration. And this is the code that does the scan that tells us how many keys are less than I for each I. All right, so the final part is the trickiest. Let's let Y be the output array. So the way this works is that now counts I tells us the first index in the output array Y where we should put items with the key I. So we're going to walk through the array X from start to finish. And we're going to take each item in turn, and we're going to copy each item into its proper place in the output array Y. And we're going to use this counts array to tell us where each item goes. So here's how that works. Here's the output array Y. Start at the beginning of X and move left to right through the input array. So the very first item in X has a key of 6. The counts array tells us that if something has a key of 6, it should go in location 7. So I'm going to copy that pointer to here. Now this location 7 is going to point to the same database record as up there. It's actually pointing to the same object. We're not copying the object, but I'm going to write the object here again anyway. And once I've done that, now I want to make sure that if another item whose key is 6 comes along, I don't write it into the same box. I don't want to overwrite this with another 6. So what I do is I increment the number here by 1, so that if another 6 comes along, it'll go into the next location instead of going into the same location. Let's do this again with the second item. The second item is a 7, so the counts array says that if I have a 7, then it goes into output location 8. So I copy the record, the entire, pointer to the record, into that output location. And I increment this count to 9, so that if another 7 comes along, it'll go into this box and not this one. And another 7 will come along, so that's important. Next we have a 3. So the counts array says a 3 goes in location number 3. And so there it goes. And we increment 3 for when the next 3 comes along. And we have a 0. Count says item 0 goes into box 0. We increment the 0. We have another 3. Now the counts array says that the 3 goes in location 4. And it's a good thing we incremented it so it's not overwriting the previous 3. So now that's a 5. We hit a 1. It says 1 goes into location 2. We hit a 5. It says 5 goes into location 6. We hit a 6 or a 0. That's a 0. Hit a 0. The counts array says 0 goes into location 1 now. This gets incremented to 2. Hit another 3. Count says 3 goes into location 5. And finally, we ended with the 7, and we know that goes into location 9. And magically, since we did things right, nothing collided, everything's in its proper place in the output array. And let me give you the code that does that. So again, we walk through the input array. For each item in the input array, we look up its key, then we look up its count, and once we have its count, that gives us an index into the Y array of where we should copy the item. And so, yeah, here I have a triple indirection, 3 array references in one, and you might have to stare at that line for a little while to really get the hang of exactly what it's doing. But it's doing the right thing, what I just demonstrated on the board. And then we increment the count so that next time we hit another item with the same key, it'll go into a different slot in the output array. And that's that. Very short, sweet code, although not so intuitive. Any questions about that? Any questions yet? All right, well, count and sort has the same analysis as bucket sort. It does the same thing, just a different way. So bucket sort and counting sort both take, they go at q plus n time. Where q is the number of different possible keys, and n is the number of items we're sorting as usual. Now, if q is in big O of n, well, that's when we actually want to use bucket sort or counting sort. It's that situation, because then they take linear time. Now, how do you decide which one to choose? Well, again, if you're sorting an array, counting sort is simpler and takes less memory. And because it's not dealing with a bunch of pointers or reference following through linked lists and stuff, array counting tends to run faster by a constant factor. On the other hand, if you're sorting a linked list, well then bucket sort is just a more natural way to do it because bucket sort uses list nodes. Any questions about that? All right, so the big question really is, what if these sorts are not appropriate because Q is not in the big O of n, which is a very common case in practice? What if there are way more possible values than there are keys that we want to sort? In that case, we go on to the big daddy of linear time sorts called radix sort. All right, so for instance, suppose we want to sort 1,000 items. In the range from 0 to 99,999,999. Just have a nice not round number. Now, we could use counting sort on that, but we'll need to use 100 million queues to sort the things in. And we will spend so much time initializing and concatenating empty queues that we will wish we'd used selection sort instead. So counting sort and bucket sort aren't appropriate anymore, but we can still rescue this by sorting one digit at a time. So let's try this. Instead of providing 100 million buckets, let's provide 10 buckets. Maybe more, but 10's a good start because it allows us to look at the number as a series of digits, and digits are easy to think about. Now let's start by sorting on the first digit only. And we can fix up the other digits later, but first we'll just get the big numbers into the right place for the big magnitudes. And we'll do that with bucket sort or counting sort, whichever is more appropriate, depending on whether we have an array or a linked list. And so here's a bucket sort for you. So the indices of this array represent the first digit of the number between 0 and just under 100 million. So for instance, maybe the first number that comes along is 73942039, and since its first digit is 7, I put it in the 7 bucket. Now, when I say first digit, I'm going to treat any number that's less than 10 million as if its first digit is 0. So if a number is not 8 digits long, you fill it out by putting zeros in front so that you have 8 digits. So the number 3429583, that only has 7 digits, so I treat it as if its first digit is 0. And so I take my big numbers between 0 and 100 million and I just sort them into buckets. Maybe some buckets are empty. That's okay. So, all right, I've gotten a good start. These numbers are somewhat in order, but they're not completely in order because within each chain, they're still unsorted. These numbers could be in completely the wrong order within a chain, but at least when you go from chain to chain, you've got the big idea right. So, what do we do next? Well, the obvious thing is recurse on each queue, and we could do that. And so sort them recursively on the second digit. And when you've done that, that will break them down into even smaller queues. You can sort those on the third digit. And you can keep this process up until you get to the very last digit. And now your list is totally 100% in sorted order. And there you have it, a linear time sort. In terms of the constant factor in the big O notation, though, this actually isn't as good as we can do. And the reason is we're taking these big queues and we're breaking them up very rapidly into millions of tiny pieces, and we have to recurse on each one of those pieces separately. And that gets to be really expensive. We can do better. So again, important point. This breaks it up into smaller and smaller subsets. And those will be sorted pretty inefficiently. Not asymptotically inefficiently. Just you wind up with a lot of constant factor overhead. So let's look at the problem another way, and we can get rid of this constant factor overhead and have a really fast sort. This is the clever idea. We're going to keep all the numbers in one big pile throughout the sort. Now we're still going to sort on every digit, one digit at a time. But we're not going to break up the big queue into smaller and smaller queues and sort recursively on each smaller queue separately. What we're going to do instead is we're going to sort on the last digit first and then work backward to the most significant digit. So you sort on the last digit, the least significant digit, then the next last, second least significant digit, and so on through bigger and more important digits until you do the biggest, most significant digit very last. Now, the reason this works is because bucket sort and counting sort are both stable. And as you learned from your homework, and hopefully in my lecture on bucket sort, stable means that if if two items have the same key, they stay in the same order in the output that they were in the input. So if I sort two numbers on their very last digit, and the very last digit is the only digit in which they're different, once I've sorted them in that order, they're going to stay in that same order as I sort through all the other digits. So again, once we sort on the last digit, then the number 555,552 is sorted before the number 55,555,058. And once those two numbers are put in the correct order on their last digit, since all the other digits are the same, and since all the remaining passes of bucket sort will be stable, these two numbers are going to stay in this order as we sort on more and more significant digits. So these remain sorted. So let me demonstrate this by sorting a bunch of 3-digit numbers. So suppose I first sort on the ones digit. Then I wind up with these numbers. Okay, so you can look through those numbers and you can look at the last digits and see they're sorted on the last digit, 0, 1, 2, 4, 5, 7, 8, 9. But the other digits have been ignored during the sorting pass. They're kind of irrelevant. So now we do a second pass where we sort on the tens. And now numbers that have zeros as the middle digit move to the front, including 5, which is really 005. And the 2s. So you can already see the stability of this sort in effect, for instance, in the fact that 771 is still before 777. They got sorted correctly during the first pass, and because the second pass is stable, they just stay sorted. And finally, we sort on the hundreds digit. And now 5 moves to the front. And 28, their first digits are both 0. And again, the reason why they're in the correct order when we're sorting on the zeros or the hundreds digit is because 5 was moved before 28 during the second pass. You can see 771, 777 still in the correct order because they've been through 2 stable passes now. And that's it. They are now in sorted order, unless I've made a typo. Any questions? Yeah?
What's the running time of the charger?
Well, in short order, it's usually big O of n, but I'll get into a detailed analysis of it in a minute.
I was wondering why it's not like n log q, for instance.
Well, why is it not n log q? It's really more like n over log because the more queues you have, the faster this goes in a way. Well, we'll see in the analysis, and hopefully that will answer your question. Yeah?
Is this faster than quicksort?
Yes. This is faster than quicksort. Certainly if n is large enough at any rate, yes. Other questions? Okay. Before I analyze the algorithm, let me point out a few other things. One is that here I've sorted on 1 decimal digit at a time. I didn't have to pick 1 decimal digit. So this algorithm, especially if I have, say, 1,000 keys, each ranging from 0 to 100 million minus 1, it's a lot faster if I sort on 2 digits at a time. Or in other words, we use 100 queues, and we treat our number as if it has radix 100. Radix is another word for base. So I had the TAs give you, at the beginning of the semester, a brush up on how to convert between numbers of different bases. And you use that in your hash table homework. So what I'm saying here is that we're still going to sort the numbers 1 digit at a time, but now I'm using base 100 digits. So you can think of a number between 0 and 99,999,999 as being 8 decimal digits, or you can think of it as being 4 base 100 digits. And if you want to sort on base 100 digits, then you have to use 100 queues instead of just 10. But if you're sorting 1,000 items, we can afford 100 queues. That's not a big deal. Or you might even sort on 3 digits at a time, which would mean we're using a radix of 1,000. So now you have to initialize 1,000 queues, but now you only have to do 3 passes to sort 8-digit numbers. Now, this is base 10 and not even 100 and 1,000 are natural for us humans to think about, but computers prefer base 2 for the most part. On typical computers, there's some exceptions, but the ones that you program every day, they like to think in base 2, and it's much faster to use a power of 2 radix. Like 256 is a particularly good radix, because if you choose 256 as your radix, then you're reading the data 1 byte at a time. Now, power of 2 radices are just more easy to extract from a key for a computer, because a computer can use its internal bit operations to get those keys, like 1 byte at a time, much more quickly than it can extract base 10 digits from a number. And you'll learn about bit operations in detail in CS61C. I don't want to get into any detail on them here, but the main point is power of 2 radices, you can extract them out of keys much, much faster on most computers than any radix that's not a power of 2. One thing I want to remind you of, again, people often get confused about Q because it serves several roles at the same time. This number Q is both the number of buckets we use in the bucket sort or the counting sort, and at the same time, it's the radix of the digit that we have to extract to use as a sort key. So you have to think of your items as being base Q numbers to radix sort them. Any questions about that? All right, let's analyze the running time. So the real question, in a sense, is how many passes we have to perform. Because we know how long it takes to do one pass of counting sort or bucket sort. The question now is, how many times do we have to do counting sort or bucket sort? Well, if you choose q q's, and it's a power of 2, then even if it's not a power of 2, well, that's less intuitive, each pass inspects the logarithm of q, the base 2 logarithm of q, bits of each key. Let me give you a concrete example of what that means. Suppose q is 256. Well, an int is expressed as (32 bits). And if you take 256 q's, then that means you can deal with the logarithm of 2 of 256 equals 8 bits in one pass. So on the first pass, you can sort on these bits. In the second pass, these bits. And on the third pass, these bits. And on the fourth pass, these bits. So having a 32-bit int and being able to sort 8 bits at a time means you have to do 4 passes. More generally, if you have QQs, then you can inspect log 2 bits and sort on log 2 bits for each pass. And then, let's assume that all the keys are represented in B bits. Then the number of passes is this, the ceiling of B over log 2 of Q. So again, the idea is you just take the length of the thing you're sorting, that's B, and you divide it by the number of bits that you can inspect in one pass, which is log 2 of Q. And I take the ceiling because you can't do a fractional number of passes. If you are able to sort on 8 bits at a time and your keys are only 4 bits, well, you can't do half a pass. You still have to do one whole pass. So that's why we have the ceiling there. And so now the question is, how do we choose Q? Because we get to decide how many Qs we're going to use. Actually, before I say that, let me just give the running time of a radix sort. They go of, you multiply the time to do one pass of bucket sort or counting sort, and plus Q, times the number of passes you have to do, which is ceiling of B over log 2 of Q. All right. Any questions on that? Yeah. Yeah.
I'm sorry, what was n plus q?
N plus q is the amount of time it takes to do one pass of bucket sort or counting sort. And then we multiply that by the number of passes we have to do. Other questions? Yeah.
What if key is floating point?
If key is a floating point, the IEEE floating point standard has been designed so that you can radix sort them, but you do have to do one special little trick. You have to do a pass at the start where you go through all the floating point numbers, and if the number is negative, you have to reverse all of its bits except for the sign bit. Then you can radix sort the floating point numbers just as if they were integers. Then you have to go through and do a post pass again that once again flips all the bits of all the negative numbers. And radix sort, the IEEE floating point standard was specifically designed so you could radix sort it. Anyone else? Yeah.
Since this is like faster than quicksort, it's like really well known like in sorting algorithm world.
Radix sort is very well known, yeah. I'm not sure why quicksort is used so much more than radix sort. It seems like partly people just have a prejudice. Some people just can't get their heads around sorts that are not comparison-based sorts. So I think radix sort gets underplayed, but a lot of the big supercomputer library sorts actually use radix sort because it's the fastest for their purposes. The Crays, during their heyday, they all used radix sort as their library sort because it was faster than quicksort and easier to parallelize in some ways. Yeah.
Is this running time comparable to n big O of n?
Well, that depends on how you choose Q. So that's going to be the next thing to talk about. See, we've got a Q here. We've got a Q here. This Q is making our running time worse, and this Q is making our running time better. So there's kind of a trade-off at what the optimal Q is. But we get to pick Q. We get to decide how many buckets we're going to use to bucket sort. So the question is, how do we choose Q so that we get good results? So let's look at the two countervailing pressures on Q. How do we choose Q? Well, on the one hand, there's this. We don't want this to be bigger than n, because it's just no fun if passive counting sort spends all its time concatenating empty Qs. So to keep that part from blowing up, we're going to choose Q to be in big O of n. And that way, each pass now takes linear time. On the other hand, we want Q to be large enough to make this part small. The bigger Q gets, the smaller the number of passes is. So we want to choose Q as big as we can, subject to this constraint. So, that's the other constraint that we want to satisfy. And so, it probably will come as no big surprise that I'm going to suggest that you choose Q to be approximately equal to n. When I say approximately, well, you want Q to be a power of 2. So you don't choose it to be exactly n if it's going to make it hard to do the bit masking operations that are going to extract your digits quickly. So we want Q to be a power of n. So if we make a choice where Q is, proportional to n within a constant factor, then now radix sort takes going to go of n plus b over log n times n time. And this first n here is because of the ceiling, the fact that the number of passes can never go below 1. But subject to that, then you've got the second term, which actually grows slower than linearly. Well, it depends on how big b is. So, for things like ints, b is technically a constant. Or longs, or floats, or doubles, or whatever. Now, sometimes you want to radix sort more complicated things like strings, or maybe extended precision floating point types. But even for those, it's generally a reasonable model to assume that the number of bits grows maybe with log n. If n is getting really huge, you'll need more bits to represent all the different kinds of numbers that you can have. But typically b doesn't grow faster than log n. And so we can just treat this as a constant. And so in that case, radix sort takes linear time. Now your practical choice of q is to make qbn rounded down to the next power of 2. And that'll work well for almost, the vast majority of situations. That'll give you a nice fast sort. Sometimes you are more interested in keeping memory use low than speed, and if that's the case, you have an alternative choice of giving up a little bit of speed to keep memory use as low as possible, and that is make q roughly proportional to the square root of n. And the interesting thing here is that the square root of n, when you plug it into a logarithm, that only changes the number of passes by 2. So we can use way fewer buckets than n. We can use square root of n buckets instead of n. And that just means we have to do twice as many passes. So it's a pretty reasonable trade-off to save a lot of memory there and maybe have to double your running time at the worst case. In that case, you might round that to the nearest power of 2. And that's how I'd suggest doing it in practice. Any questions on that? All right, well, happy Thanksgiving, everybody. See you Monday.